In this particular situation here with our systems of linear equations, we are only looking at the two kind of unusual solutions. All right, when we graph a system of linear equations and they cross, then the ordered pair is the answer. Okay, that's the obvious one, that's the easiest one. All right, but we could also have two lines when we graph them, and I am going to use a ruler, and I'm just going to randomly place a line here. Let's go 1, 2, 3, 4 on the y-axis, and then let's go 1, 2, 3, -3 on the x-axis. All right, and then let's draw a line there. So we could graph one of our linear equations, and it end up being right there with the x and y intercept. And then when we graph our second line, let's say it is maybe at, let's put a dot at -1, -2, and then let's put our other dot at 2, 2. And then when we graph that second line, it might end up like that. Okay, so when we graph two lines, they don't have to cross, they could be parallel. If they are parallel from last week, do we remember what we said this was last week? This one is no solution because the two lines will never ever cross, they are parallel. So you literally have to write no solution down. Okay, if you get two lines and they turn out to be parallel, it is a no solution. Okay? So this is like special case number 1. All right, now special case number 2. Let's suppose we graph a line and it turns out, let's put a dot at 1 on the x-axis, and then let's put a dot at, say, 3 on the y-axis. So when we graph a line over here, let's say that it ends up right there. And I'm going to do this one relatively short for a reason. Okay, because we could graph one line, and then when we graph the second line, it could end up being on top of the first line. So that's why I did this, and we'll try to use two colors here so that maybe you can tell that that means, like, see, the first line was the black line, second line was the red line, one line right on top of each other. Okay, so where you put it on your graph, it doesn't necessarily have to be precise. I see some of you kind of squinting to see where I put it. All right, I went through 1 and I went through 3. All right, the point is, if you graph one of the lines, and then when you go to graph the second one, it ends up being on top of the original graph, then this one, we generally, I will let you as a shortcut just write IMS, but I want you to know what IMS stands for. That stands for infinitely many solutions. Okay, now stop and think about that. Infinitely many solutions. I don't think we've ever talked about this year, but you probably did in previous years. How many points are on that line? A lot. How about, can I count them? No, I can't, because there's infinitely many points on that line. A line goes on forever and ever in both directions. There's infinitely many points on that line. All right, now, when we graph the two lines and they cross, how many points do they cross at? 1. So that's why we write the ordered pair. But since one line ends up on top of the other line, how many points do they have in common? A lot. Every one of them. Infinitely many of them. So this one, we couldn't write down all the ordered pairs because there's too many. When they cross, and they cross only at one spot, we write down one ordered pair as the solution. But this one, every point on that line is a solution because they landed on top of each other. So then, shortcut, we just write IMS. All right, but if you write IMS and you don't know what it means, that's not any good. So I need you to understand infinitely many solutions and why it's infinitely many solutions. Okay, so these are your two exceptions to graphing a system of linear equations, because if they don't cross, then they're either going to be parallel or they're going to be the same line. Okay, all right, so pretty simple, straightforward there. Okay,